The general contractor's proposed lightning protection system involves installing lightning rods at the top and ground rods at the bottom of each column, all along the outside edge of the building. These components will create a direct path to ground for lightning strikes, providing a safer environment for occupants and equipment. While the lightning protection system will provide a preferred path for lightning strikes, it is not guaranteed to completely prevent strikes or eliminate all risk. Lightning can still strike the building in other locations, especially if the system is not properly designed or installed. Concrete is a poor conductor of electricity compared to metal. However, it can still provide some level of conductivity, especially when moist. The concrete piers drilled 80 feet into the ground can help improve the grounding system by providing a larger surface area for current dispersion. The 80-foot depth of the concrete piers will enhance the grounding system by providing access to lower resistance soil layers. This will facilitate the dissipation of lightning current into the earth more effectively. The lightning rods attract lightning strikes and direct the current to the ground rods. They provide a preferred path for lightning to follow, thereby reducing the risk of damage to other parts of the building. Ground rods are driven into the earth to create a low resistance path for lightning current to dissipate into the ground. They provide a way for the electrical energy to safely discharge without causing harm. The lightning protection system must be properly designed and installed according to accepted standards and local codes to ensure its effectiveness. The system should be inspected and maintained regularly to ensure its proper functioning. The metal structure of the building will also contribute to the grounding system. However, it is important to ensure that all metal components are properly bonded together and connected to the ground rods. In certain areas or for critical facilities, additional lightning protection measures may be necessary, such as surge protectors and lightning arresters. Considering the information provided, several points need clarification and expansion to provide a comprehensive understanding of lightning protection systems, specifically concerning the interaction with concrete, grounding depth, and overall system effectiveness. Firstly, addressing the effectiveness of a lightning protection system. It's crucial to understand that such a system does not offer absolute immunity from lightning strikes. Instead, it significantly reduces the risk of damage by providing a preferred, low-impedance path for the lightning current to follow to ground. This controlled path minimizes the likelihood of the current traveling through less conductive and potentially damaging routes within the structure. Secondly, the role of concrete needs further elaboration. While concrete is indeed a relatively poor conductor compared to metals like copper or steel, its conductivity is not negligible, especially when it contains moisture. The presence of rebar within the concrete structure further enhances its conductivity. The deep concrete piers serve a dual purpose. Firstly, they provide a substantial surface area in contact with the earth, facilitating current dissipation. Secondly, the depth of 80 feet may reach soil layers with lower resistivity depending on the local geological conditions, thus improving the grounding system's performance. Thirdly, the improvement provided by lightning rods and ground rods is based on several principles. Lightning rods, or air terminals, are designed to intercept lightning strikes. Their placement at the highest points of the structure increases the probability of a strike hitting them rather than other parts of the building. The captured current is then directed through conductors to the grounding system. Ground rods, typically made of copper or copper-clad steel, are driven into the earth to provide a low-resistance path for the lightning current to dissipate. The effectiveness of ground rods depends on factors such as soil resistivity, rod length, and the number of rods installed. In high-resistivity soil, multiple ground rods connected in parallel may be necessary to achieve an acceptable grounding resistance. Fourthly, proper bonding and grounding are essential for the overall effectiveness of the lightning protection system. All metallic components of the building, including the metal structure, piping, and electrical systems, should be properly bonded together and connected to the grounding system. This bonding minimizes potential differences and reduces the risk of side flashes, which can occur when lightning current jumps from one metallic object to another. Fifthly, the design and installation of a lightning protection system must comply with relevant standards and codes, such as those published by the National Fire Protection Association, specifically NFPA 780. These standards provide detailed requirements for system design, component selection, installation methods, and maintenance. A qualified lightning protection system designer should be consulted to ensure that the system meets the specific needs of the building and complies with applicable regulations. Sixthly, regular inspection and maintenance are crucial for ensuring the continued effectiveness of the lightning protection system. Inspections should be performed periodically, typically annually, to check for any damage or deterioration of system components. Ground resistance measurements should also be taken to verify the integrity of the grounding system. Any necessary repairs or replacements should be performed promptly. Seventhly, additional protection measures, such as surge protective devices, SPDs, can be used to further reduce the risk of damage from lightning strikes. SPDs are designed to divert surge currents away from sensitive electronic equipment, protecting them from damage. SPD should be installed at the service entrance and at downstream panels to provide comprehensive protection. Eighthly, considering the information about Hawthorne, New York, it's important to account for local soil conditions and lightning strike frequency. Soil resistivity in the area may vary, and a soil resistivity test should be conducted to determine the optimal grounding system design. The lightning strike frequency in the region should also be considered when assessing the overall risk and determining the level of protection required. Ninthly, the NEC, specifically the 2014 edition reference, provides guidance on grounding and bonding requirements for electrical systems. While the NEC does not specifically address lightning protection systems, its grounding and bonding principles are relevant and should be followed to ensure a safe and effective installation. Tenthly, addressing the specific question about the impact of the 80-foot deep concrete piers, their depth is indeed beneficial. Deeper grounding electrodes generally encounter lower soil resistivity, as soil tends to be more compact and moist at greater depths. This lower resistivity facilitates better dissipation of lightning current into the earth. 11thly, the CAD-welded connections mentioned are a reliable method for creating low-resistance connections between conductors and grounding electrodes. CAD welding, also known as exothermic welding, creates a molecular bond between the metals, resulting in a permanent and corrosion-resistant connection. 12thly, it's crucial to ensure that the lightning protection system is properly coordinated with other building systems, such as the fire alarm system and the electrical system. This coordination minimizes the risk of false alarms or other unintended consequences during a lightning strike. 13thly, the design of the lightning protection system should take into account the specific characteristics of the metal structure, including its height, shape, and orientation. The number and placement of lightning rods and down conductors should be determined based on these factors. 14thly, the use of corrosion-resistant materials is essential for ensuring the long-term reliability of the lightning protection system. Copper, copper-clad steel, and stainless steel are commonly used materials for lightning protection components due to their resistance to corrosion. 15thly, the grounding system should be designed to minimize ground potential rise during a lightning strike. Ground potential rise is the increase in voltage potential of the earth surrounding the grounding electrode during a lightning strike. High ground potential rise can pose a safety hazard and can damage electronic equipment. 16thly, surge protection should be provided for all incoming power, communication, and data lines to protect against lightning-induced surges. These surges can travel through wiring and damage sensitive electronic equipment, even if the equipment is not directly struck by lightning. 17thly, the lightning protection system should be designed to minimize the risk of step potential and touch potential hazards. Step potential is the voltage difference between 2 points on the ground that are a meter apart. Touch potential is the voltage difference between a grounded object and a point on the ground that can be touched simultaneously. 18thly, the lightning protection system should be designed to minimize the risk of fire caused by lightning strikes. Lightning strikes can ignite flammable materials such as wood, paper, or gas if the lightning current is not properly conducted to ground. 19thly, the lightning protection system should be designed to minimize the risk of explosion caused by lightning strikes. Lightning strikes can ignite explosive materials such as gasoline, propane, or natural gas if the lightning current is not properly conducted to ground. 20thly, the lightning protection system should be designed to minimize the risk of mechanical damage caused by lightning strikes. Lightning strikes can cause structural damage to buildings, such as cracks, holes, or collapses, if the lightning current is not properly conducted to ground. 21stly, the lightning protection system should be designed to minimize the risk of electromagnetic interference caused by lightning strikes. Lightning strikes can generate electromagnetic fields that can interfere with electronic equipment, causing malfunctions or damage. 22ndly, the lightning protection system should be designed to minimize the risk of injury or death to people caused by lightning strikes. Lightning strikes can cause serious injury or death to people who are in or near a building that is struck by lightning. 23rdly, the lightning protection system should be designed to comply with all applicable codes and standards such as NFPA 780 and UL 96A. These codes and standards provide detailed requirements for the design, installation, and maintenance of lightning protection systems. 24thly, the lightning protection system should be installed by a qualified and experienced contractor. A qualified contractor will have the knowledge, skills, and equipment necessary to install the system properly and safely. 25thly, the lightning protection system should be inspected and maintained regularly by a qualified contractor. Regular inspections and maintenance will help to ensure that the system is functioning properly and that any problems are identified and corrected promptly. 26thly, the lightning protection system should be designed to take into account the specific characteristics of the building, such as its size, shape, height, construction materials, and occupancy. The design should also take into account the local climate and soil conditions. 27thly, the lightning protection system should be designed to protect all parts of the building, including the roof, walls, foundation, and interior. The system should also protect all equipment and systems within the building, such as electrical systems, plumbing systems, and communication systems. 28thly, the lightning protection system should be designed to provide a safe and effective path for lightning current to flow to ground. The path should be as short, straight, and direct as possible. 29thly, the lightning protection system should be designed to minimize the impedance of the grounding system. The impedance of the grounding system should be as low as possible to allow lightning current to flow to ground easily. 30thly, the lightning protection system should be designed to minimize the risk of corrosion. Corrosion can damage the system and reduce its effectiveness. 31stly, the lightning protection system should be designed to be aesthetically pleasing. The system should blend in with the building and not detract from its appearance. 32ndly, the lightning protection system should be designed to be affordable. The cost of the system should be reasonable and should be weighed against the benefits of protecting the building from lightning damage. 33rdly, the lightning protection system should be designed to be environmentally friendly. The system should use materials that are sustainable and that do not harm the environment. 34thly, the lightning protection system should be designed to be durable. The system should be able to withstand the elements and to provide many years of reliable service. 35thly, the lightning protection system should be designed to be easy to maintain. The system should be easy to inspect and to repair. 36thly, the lightning protection system should be designed to be safe for people to be around. The system should not pose any risk of injury or death to people who are in or near the building. 37thly, a lightning protection system should be designed to be effective in protecting the building from lightning damage. The system should be able to prevent lightning strikes from causing fires, explosions, or other damage. 38thly, the lightning protection system should be designed to meet the needs of the building owner. The system should be tailored to the specific needs of the building and the owner's budget. 39thly, the lightning protection system should be designed to provide peace of mind. The owner should have confidence that the system will protect the building from lightning damage. 40thly, the effectiveness of the lightning protection system can be further enhanced by implementing a lightning warning system. A lightning warning system can provide advance warning of approaching lightning storms, allowing people to take precautions and move to a safe location. Finally, it's important to remember that lightning protection is a shared responsibility. Building owners, designers, contractors, and occupants all have a role to play in ensuring that the building is protected from lightning damage. In conclusion, while the proposed lightning protection system will provide a safer environment for the building, it does not guarantee complete immunity from lightning strikes. Other factors, such as the building structure, grounding depth, and maintenance, also contribute to the overall effectiveness of the system.